for our examples on the back, continuing on with 10.4, taking a look at example 4, it says you've decided to take advantage of a meal deal at a local restaurant. So you've probably seen ads like this before. I know Applebee's and Chili's and things like that sometimes have their 2 for $20, where you get 2 meals that include an entree and an appetizer or something for $20. So this is the situation we're looking at. The meal deal includes soup for each person, and there are 2 available choices of soup. An entree from menu A, an entree from menu B, and then a dessert for each person. Now, we have different entree menus, so one person has to choose from menu A and one person has to choose from menu B. The difference here is that we have different amounts of choices for each of those menus. They get the same choices for soup and the same choices for dessert, but they have different entree choices. So how many different possibilities are there? How many different options are there for dinner? The first thing I need to consider is that I've got 2 people. And so that means that one person's going to choose from each menu. So I have to consider 2 options. My first person chooses from menu A, which would mean the second person chooses from menu B. I would also then have to consider if the first person chooses from menu B and the second person chooses from menu A. So we're going to start off with person 1 picks from A, menu A. So if that's the case, then for person 1, their options would look like this. They have 2 choices for soup. They have 10 choices for entrees. And they have 4 choices for dessert. For person 2, they would have the same 2 choices for soup. However, they only have 9 choices for entrees. And then they have the same 4 choices for dessert. So this is fundamental counting principle, which we talked about earlier this week. When I multiply here, I end up with 80 options for person 1 and 72 options for person 2. Now, to figure out our total number of options, the total number of ways that this could happen, total number of choices that we have available, we're again going to have to multiply. Person 1 is going to choose one of these 80 options, and for each option that person A chooses, person B can then pick one of their 72 options. So if I drew a tree diagram for this, I would have 80 branches for person 1, and then off of each of those 80 branches, 72 branches for person 2. So this is, again, fundamental counting principle. We are multiplying our available choices together to figure out our total. So that would be 5,760. Now, remember that this is only the case where person 1 chooses from menu A. The other option that we have is that person 1 picks from menu B. Our work is going to look similar, but we have to consider all of our options. So this time for person 1, they would still have 2 choices for soup, but now only 9 choices for their entree, still 4 choices for dessert. Person 2 will have 2 choices for soup, 10 choices for entree, and 4 choices for dessert. Notice that I've basically just swapped the work for person 1 and person 2 over here. So person 1 will have 72 options, person 2 will have 80 options. Whichever option person 1 picks, person 2 would still have each of their 80 options. So again, we would have that big giant tree with lots of branches to figure out our total number of options. We would multiply and get 72 times 80, which would be the same as 72 times 80 over here, so 5,760. So that means if person 1 picks from menu A, I have 5,760 options. If person 1 picks from menu B, I have 5,760 options. To figure out our total possibilities, we're going to add these 2 options together. We're not multiplying here because if person 1 picks from menu A, then I don't have these options. If person 1 picks from menu A, then all of these options are eliminated. When I talk about before anybody has chosen my total options, I would have all of these options and all of these options. So our total possibilities before anybody orders would be 11,520. The last thing we're going to talk about are distinct arrangements. Distinct arrangements are something that we need to specify when we have repeated items in a group. Repeated items are typically indistinguishable. If we think about the name Sarah, there are 2 A's in this name. If I switch places of letters and I write A-R-A-S, that's clearly a different arrangement of this name. But if all I do is swap the places of the A's, so let's say I moved this A over here and this A over here, I still have the name Sarah. So these are not distinct arrangements. So if I have repeated items, I need to account for that when I talk about permutations of those items. So suppose I have a set of however many objects that are R different types. So I've got some kind of repeats. If N and R are the same number, you would have no repeats. But if R is a number smaller than N, then you do have some repeated elements, like we have repeated A's in the name Sarah. So for however many objects I have of each type, I need to account for that in my permutation formula. So we do that with a modified permutation formula for distinct arrangements. We start with our same n factorial that we had the other day when we talked about permutations, but then we divide by the factorial of the number of elements that each object has. So that's our formula, and then we'll take a look at an example. The formula makes a little more sense when you have it in the context of a problem. So for example 5, an anagram is a word which is made up by rearranging letters. For example, stop has an anagram in the form of post, which also has an anagram in the form of pots. So when I can rearrange the letters in a word to make a new word, that's called an anagram. I want to know how many potential anagrams of this word are there. I say potential because some of our rearrangements won't actually be words, but we want to look at how many potential options we have. So how many potential anagrams of mini are there? So the first thing we need to know is how many letters do we have? How many total letters in the word mini? Number of letters is our n. So we've got 1, 2, 3, 4, 5, 6. 6 letters. And then to figure out our N1, our N2, our N3, so on and so on, we look at how many distinct letters do we have. We do this without respect to capitalization. So I have an uppercase M. If I had a lowercase m, I would not distinguish between those two. So I have an uppercase M. I just have one of them. Since that's the first letter I see, I'm going to call it N sub 1. And there's only one of them, so N sub 1 would be equal to 1. The next letter I see is an I. I have 2 of those. Since this is the second letter I see, I'm going to call it N sub 2. And since there are 2 of them, it's equal to 2, right? 2 I's in mini. The next letter I see is an N. Since it's the third letter, I'll call it N sub 3. And I have 2 N's, so N sub 3 would be equal to 2. Now we have another N, but we've already counted N's. We have an I, but we've already counted I's. And then the last letter we see is an E. Since this is the 4th distinct letter I see, I'm going to call that N sub 4. And there's just one of these, so N sub 4 would be equal to 1. Now for our formula, we'll take N, no subs, just plain old N, factorial, so 6 factorial, and divide by each of my sub-factorials. So 1 factorial times 2 factorial times 2 factorial times 1 factorial. Now 1 factorial is just going to be 1. So is it super necessary to write 1 factorial? Not really. What we really have is 6 factorial over 2 factorial times 2 factorial. But the ones don't hurt anything, so it's okay if you write them in there. When you simplify this in your calculator, remember 6 factorial divided by 2 factorial times 2 factorial. Use parentheses if you feel you need to. It's always a good idea to use parentheses when you've got more than one thing happening in a denominator. When you divide this in your calculator, you should get 180 distinct arrangements. Distinguishable permutations, you may also see this called. So there are 180 ways that I can rearrange the letters in the word mini that I will be able to tell apart. So that does not count if I just swap the places of the N's, or if I just swap the places of the I's, or if I were to rewrite it I, N, N, I, E, M, and then swap the places of the N's or swap the places of the I's.